First, I need to find myself the link to the GitHub. Sorry about that. I need to restart everything, and now I need to log into everywhere. Okay, now we can start. So we're going to have now tutorials on the galactic binaries. I have some visual explanation how it looks like to analyze galactic binaries. We're going to analyze one galactic binary, and this looks like a, playing with a little kitten. Also, we're going to fix most of the parameters and only vary some of the parameters and only fit these parameters. But in reality, analyzing galactic binaries is like you are locked in a room with a lot of angry cats. So it's a bit different, because the reason is that in reality, probably you saw in some lectures that there are millions of galactic binaries, thousands of resolvable ones, and then usually we analyze them kind of band by band, by narrow frequency bands. And then if you take really narrow frequency band, you can see a picture like that. So you can see like 10 of these galactic binaries overlapping with each other. So in principle, it is a very complicated problem, and this is kind of one of the reasons why we're doing this global fit and reversible jump, because we don't know how many signals they are. But in these tutorials, we will try to do just one galactic binary, because otherwise, it will be a bit excessive. But we will try to do things a bit different compared to what Kantan did. So we will do part using MCMC parameter estimation in a similar way that Kantan has done for massive black hole binary. The difference here is that we will not write the likelihood ourselves. We will try to use the software that exists and kind of try to learn to use this software to plug in our waveforms and our data into that. And we will also have a bit of machine learning here. First, we will do the search with machine learning. So in principle, if you have the data set and only one galactic binary in that, you maybe don't even need to do the search. But in general, as Stas also told in the lectures, usually the data analysis is separated into search and parameter estimation. And here we will try to do two different machine learning things. One is the thing that is very similar to the search one, and that can be used as a search, which is a point parameter estimation. And then after doing the parameter estimation with MCMC, we will try to do the Bayesian parameter estimation with normalizing flows. Some people might have been on the Manitou summer school, so some of the tutorials will be similar to that. So if you have been there, help your friends, because you definitely know how to use everything already by this time. And I just want to mention that the same as for the massive black hole binaries, we are going to use the accelerated waveforms. So in reality, the kind of the simplest and most straightforward thing, what you would do, you would write h plus h cross of the waveform that for galactic binary is a almost monochromatic signal, so some sort of sine wave which slowly changes its phase. And then you will apply you will project it on the sensitive axis of the detector. You will apply the TDI, and that's how you create your waveforms. But of course, this all takes time, and this is not the fastest way to do this. So people, thus far, the way people have been analyzing the data was in the frequency domain, and there are frequency domain fast waveforms that are explained, the way they work is explained in the appendix of this paper. And there are a couple of implementations of these waveforms. Some of them are called FastGB, and this is GBGPU implementation, which is a re-implementation of the FastGB waveform. So let's start with the first tutorial. So I just wanted to give like a very brief introduction of what we're going to do. So if you think of a very simple, straightforward way you can apply machine learning to estimating the parameters, is that you have some sort of network, any network you want, fully connected network or CNN, and then you, as your inputs, you put the simulated data. So you create your waveforms, you add the noise to the waveforms, and for each simulated data set, you know the parameters that you used while you were creating this data set. So your output of the network would be these parameters that were used while you were created the simulated data, which are quite often called labels, these outputs. So you train your network like that, and then you give it the real data, and it has to give you the prediction for these parameters. So the way you construct this network, so as I said, it can be any kind of architecture. What is important is that usually in the last nonlinearity for the output, you should use some sort of linear function nonlinearity, and then for the cost function, it will be some kind of mean square error. That's what we are going to implement in our first tutorial. And yes, the thing here is that you can see this implementation as a search, because it gives you just one value. And also compared to the kind of classical approach, the problem here would be also that your estimation might be biased by the error estimation of your network. But this approach can be really fast and can be useful in the case you do the search. Are there any questions at this point? Okay. Mm-hmm.
Is this approach used anywhere in the analysis of gravitational wave data? Or is it just a simplified case that we do in this tutorial? Oh, sorry.
For now, no. Not by in this, as far as I know, but I want to use it. So that's just there are so many things to do, and I never came to actually implement it for a more realistic case. But I think it's very useful as a search because it can be really fast. You can find, and then as Kantan was showing you in the tutorial, he he said that he is cheating in the end and that he is starting close to the true point. So, and this true point you get from the search, so one or the other search. And also for MCMC, to speed it up, everyone uses, in LISA at least, the so-called heterodyning or relative binning. I don't know if you have been told about this on the lecture by Stas. No, probably not. So this is sort of the way you think you kind of almost found the correct waveform, and this is as if you're writing linear expansion around the correct waveform, and like that you can use less frequencies to evaluate your likelihood. And for that you also need to have your reference template. So search can be really help to speed things up. Yeah, but there is a lot of potential in LISA data analysis. Not many things have been tried yet. So let's try to do this tutorial. So here we are going to use this GBGPU waveforms, but we are going to use a kind of lightweight version of them. Also, one comment, so I don't know, for me it's not going to work, I think, because when I was testing, I was already using GPU, and now it doesn't allow me to do this. But you can choose here in your, sorry, it's in French, but in execution, you can change the type of execution, and you can choose the GPU. And then this will work much faster. So unfortunately, after some time, if you use it, it will ask you to pay for it. So,
sorry, can you show again?
So it's here execution.
Put a runtime in English.
Okay.
Put a runtime in
Runtime. Yeah, so modify the type of runtime, yeah? Or just runtime.
Change runtime.
Change runtime. Yeah, and here you choose GPU. I try to write the code that it is agnostic, so you can run it both on CPU and on GPU. So I already installed it. Then we do some installations, corner plot to do some plots. I also have some re-implementation of the noise from LDC, just not to install all the LDC for that. Then we run, we install Torch, so we're going to use PyTorch for that, which is very straightforward, very close to Python. And then here we are going to use some sort of wrappers so that the code would be agnostic to the use of GPU or CPU. Then we need to prepare our training data. So our training data would be our waveforms plus noise. The galactic binary waveforms, they're quite simple. They're parameterized by 8 parameters: the amplitude, initial frequency. Then for some galactic binaries, it's possible to measure the f dot, the change of the frequency. Then the initial phase, the position of the orbit, the inclination of the orbit and polarization angle of the orbit, and the position of the source on the sky, lambda and beta. The same as for massive black hole binaries, we're going to use A and E TDI channels. And in some sense, here because for machine learning you don't write the likelihood, it is a better way, in a sense, to include all these correlations between the noise and non-Gaussian noise. So in this case, if you take A and E channels and they would have a correlated noise, that will not be such a problem.
So it's a question. Where is the mass of the binaries encoded?
Mass, so mass is in the amplitude, and you can say the chirp mass is in f dot. I think amplitude has a chirp mass also in it. Okay, and so we're going to create these waveforms, and then we're going to do the simple thing of producing the realistic noise. So we are going to take the power spectral density, and then we're going to sample the noise realization from this power spectral density. And we are going to fix all parameters except two, except the sky localization, to make it faster and easier to train. So let's do this. So we say that we create 10 to 4 training samples. We define these samples that we're going to sample as just like randomly sampled from the uniform distribution. Often for the ecliptic, this is ecliptic latitude, it will be uniform in sine beta, but here for simplicity we just use uniform. Then we fix some parameters, and here I chose parameters of one of the verification binaries. And these will be true parameters. This we just need to have them to create the kind of observed data set, put it to the network, and see what the network would predict us, and then compare it. Okay, so we stack the parameters that we are going to sample. So these are two parameters that we are going to sample, and the other ones are fixed. Then we put together all the parameters, because this is what we need to pass to the waveform generator. Then we define the observation time. Here we put 1 year, and for DT we put 15 seconds. This is the number of points around F dot. So the thing is that galactic binaries, they are really narrow. They are almost monochromatic. So to produce a galactic binary waveform, we need just an order of 100 frequency points. And it depends in which frequency range this galactic binary is located. So for some frequency ranges, maybe it's even enough to have 64 points, and for some it's 256, but it's a very, very narrow. So here we create all the waveforms together, because this the advantage of this waveform implementation, and I think FastGB also have it now, that we can create the waveforms in batches. So if we define here the parameters, they are given in batches. So we each of these variables is 10,000 points vector, and when we pass this to the waveform generator, it would create us 10,000 waveforms, which is very good. It speeds up a lot everything. And then what we need to do, we need to define our frequency band in which we are going to place our template. As I said before, because we have these 10,000 signals, we don't analyze them all at the same time. And also because they're very narrow band, we can just take bands, and in each band, let's say, we'll have an order of 10 signals. And we analyze usually galactic binaries band by band. And here we define this band around the F naught. And we here we sample our PSD. We plot our PSD for this frequency range, which is a linear because it's really a really narrow frequency band. And the next thing that we need to do is we need to place our waveform within this frequency band, because when we do, for example, sampling, we don't need to do this because we always have a frequency, kind of reference frequency array. But here so here with the network, it doesn't know, relative position of these waveforms. So each waveform we need to place in this band, and we need to know their relative position one to another, especially if we're estimating the F0. Let's look at how the waveform looks like. This is just one of the, this is A channel whitened real part. And now let's create our data set that we are going to use for training. It is very useful to use things like, for example, PyTorch class data set, because if you would define this class and you would define your data within this class, it will index all your data that is on your disk space, and it will only load into memory the data batch by batch. Because the problem with the GPUs quite often is that they have very limited memory capacity. And if you do it like that, you will not have to load all the data at once, so you only have to load batch by batch. And one important thing that I didn't mention is that for machine learning, you always need to normalize your data or standardize your data. So it doesn't work very well with the physical ranges of parameters. And here, for example, we are going just to standardize, subtract the mean and divide by the standard deviation. Also, we are going to take both A and E TDI channels and going to take real and imaginary parts of them. Especially this is important because we want to estimate the sky position. And we are just going to concatenate them with each other. So you see that your data set then becomes 10,000 times 4 times the number of the frequencies. And 4 is a kind of number of the channels. So each channel is either A real, A imaginary, E real, E imaginary. Now we define this data set, an instance of this data set class. Sorry, not an instance, but we kind of like implement the child of this class, which is our waveform data set. We initialize it by passing the parameters and the waveforms. And it would know that a particular index of the parameter corresponds to the particular index of the waveform. So this is the most important thing that it does, and that it will just randomly pick up the waveforms and corresponding parameters from your data set. And then at this point, we add noise because we whitened our data, so we divided by the power spectral density of the noise. We can add just a normal noise. And we return our data. And let's look, oops, let me direct this. And this is how it looks like with the noise. So it is a quite high SNR signal. Is it everything good?
Okay, so every time you ask this data set for a particular index, so like a particular waveform with parameters position in the sky, gives you a different data set because it's always regenerating the noise?
So each time, yes, each time it will wait a second. Yes, each time it will regenerate the noise, and it will the index. So you don't really care about particular index. What you care about is that, so when you would train your network, you want to go through all your data set, training data set. And you would say, like, go through data set and give me batches, random batches from the data. So it will randomly reshuffle them and then give you each time the random batch, and when it exhausts all your data set, it will say that it went once through everything. So that's how it works.
Okay, because you're only going through each of them once, it doesn't matter.
So yeah, you only see each one once, and then you can do it multiple times. So usually it's called epochs. So when you have a fixed data set, and you went once through all the data set, you say that you finished one epoch.
Are you going to, so for one signal, you pass only one noise realization for that signal? So you
Yes.
experimented with like many noise realizations for the same signal, so it's easier for you to understand that.
I mean, this is just an example.
No, I was just paper that you had done in 2024. It's not six months.
No. This is a very simple regression thing. Okay, and so now we need to define the network. And we are going to use the CNN. This is a convolutional neural network. The convolutional neural network's advantage, so to say, is that they can reduce the number of links that you have with consecutive layers. That's why you can make them deeper, and you can hopefully extract more information. And initially I thought to make an exercise to write your own network, but I don't think we have so much time. So we just, for the future, you can try to play with these different implementations, and actually sometimes it is sort of tricky thing. Sometimes it will just not work and give you, for example, mean value of your training data set. So it is interesting to play with that and see which components of the networks are important to make your training more stable. And you can see that our our input size is 4. This is 4 channels. And then these are just number of filters that we want to have, a number of the output channels. And the last layer is the linear layer. So this one is very similar to the one that I've shown you before. And it gives you as the output 2, which corresponds to the 2 parameters that we're going to estimate. So the number of outputs here have to be the number of parameters that you are estimating. Now what we do, we separate our data sets to 2 parts, training and testing. Quite often people do train, validation, testing, but here we just do 2. And because on one we will train, on the other we see how it performs. And we take the batch size of 256. Then we need to define the optimizer. For example, the ADAM optimizer is quite often used, and here we also need to define the learning rate that we use. Next, we define our loss function. So here it will be mean squared error. And now we define our training loop. So in the training loop, we go batch by batch through this data loader. And this is where it will kind of implement for us going this through like each epoch, finishing each epoch, which means exhausting the data set. Then we use the model to predict the output. And then we compare the output to the actual values of the parameters and calculate the loss. And then we do the backpropagation and output the values of the loss to see how it's performing. We have the similar thing for the test loop without backpropagation to see on the testing data how well it performs. And let's try to run it. Maybe, can I stop it? This might be too much, but I'm not sure it will. Let's try 30 epochs. Unfortunately, Because I cannot connect to GPU now, it might take some time. Because when I was running it on GPU, it was much faster. Are there any questions? Then we will take the results of this network and use them as a kind of search result and put them in our MCMC parameter estimation and start our MCMC from the point that we have found. Yes?
Oh, sorry.
You said that in principle there would be 3 stages, and you said there's one that we skip, which is validation.
Yes.
What would it be? What would consist the validation step in?
In principle, here our test data set is a validation data set. Usually the test one is called, which is the real data. So for us, our test would be when you, validation set is when you would create a simulations that would be like the ones you used for training, but the ones that the network have not seen. And then the test one would be when you give it real data and it gives you some predictions.
Okay, thanks.
Yes?
So in practice, what is the code that you should do yourself? What is it already written by someone else?
Sorry? Can
In
you?
practice, if you really want to do this in global fish, something like that, what is the code that you need to write yourself? What is already written by someone else?
What do you mean written by someone
So
else?
basically, what you can just call type without you writing yourself, and what do you have to write yourself?
So the break propagation, all that stuff is implemented in some frameworks. And what you have to write yourself is how you define your data. For example, let's say you want to analyze the real galactic binaries. In reality, you're not going to have one galactic binary. You're going to have many galactic binaries. So the idea, for example, what you can do here, with galactic binaries it's hard because there are many of them and you don't know how many they are, so it's harder to make a training data set. But let's say you have a master black hole binary. And then you take your part of data with your master black hole binary, you train it on, let's say, a range of chirp masses of master black hole binaries, you give it the data and it gives you the estimate of the parameters. The problem with the reality is that you need to take into account that there are other signals, so you probably need to do some kind of embedding of your data first, and then you need your signals, they can be long-lasting, short-lasting, so this also would make things more complicated.
So you are saying the thing only you need to implement yourself in this waveform database?
Yes, working with waveforms and compressing them, and somehow not compressing, but like embedding them. So that's, I think, the hardest part. And we are slowly getting there. Yes.
I think it's because you don't have the CPU.
I don't have GPU because
GPU?
it doesn't. When I was testing, I was running it, and now it asks me to buy time. Yeah.
Can you explain the relation between separating the test data out and then not overfitting? What is the logic there?
So we will see it now in the next cell, because when you run, like you have your training data and you run your network by showing it this training data, sometimes it can start overfitting to the particular data set. And when you show it a different realization of the data, it will give you very bad estimation. So sometimes you can see that like if your training data is very small, you would have, for example, your loss curve for your training data would go like that, but for validation data it will go like this, because you always need to check, like if it's not overfitting, and this is the next thing, should show the loss curves. Yeah.
How can verification binary be used for that?
The verification binaries is just like any other binary. So I don't think so.
I guess you can check coverage. Like you can check maybe like a posterior that you get from your method with already existing posteriors you have on verification binaries. And then you can, sorry, I was just saying that, yeah, no, you heard it.
Well, you can, yeah, you can check it also with not verification binaries.
But we don't know the ground truth, kind of. You know, we don't have an estimate. Like verification binaries, we have somewhat of an estimate of their masses, I'm assuming.
Yes, but not really. So we don't really know. And then, so some people say that verification binaries actually they are not, the brightest ones. And that, to have a good parameter estimation for verification binary, you need to estimate the parameters for all other binaries nearby, and then you have a good parameter estimation. There is a paper from Tyson about that where he says that he doesn't like the name verification binaries. Yes, so...
So they are just binary.
It is more like it's good to use them because you know that they're there, and if you see them, you are certain that you are seeing what you expect to see. But in terms of data analysis, I don't really know how they can help you.
Okay. Well, you can use a narrow range in the prior.
Yeah, if you would just look for one of them.
No, but you can say in the global field you can have a log which is...
Yeah, you can change your prior. Yes.
I'm done.
Yes, so this loss curve is a bit funky, but anyway, it's training, and you see they're kind of like following the train loss and the test loss, following each other. And this is how it should look like. I hope it looks like that. Okay, yeah. So what this plot means is that on one axis you have the true value, and on the other axis you have a predicted value for your test data. And in principle, if you would have no noise, it will be just a diagonal if you trained well your network. So it predicts you almost the same value as you put inside. And then because you have a noise, of course, you have some sort of the error. And the different colors here, I plotted one for beta, one for lambda. So it kind of worked well. It has some errors here and there, and maybe it would be narrow if you train for longer. But then what we can do is we can kind of create our true data set with the true parameters. And then we can put this, so we have to renormalize back these parameters to the, multiply by the standard deviation and add the mean. And then we see what the network predicted us. And then we compare it, like, sort of worked. But it is, of course, you cannot use this for your actual parameter estimation because this is not good enough. But what we can use it for, we can use it as a starting point, for example, for MCMC. And this is where our next notebook brings us. So the next one is sample galactic binary with MCMC. Is it okay? People are bored or are all good?
Question.
like it's written point parameter estimate, but this is really for search, right? It's not for parameter estimation.
So it's called, usually people call it point parameter estimation, meaning that it estimates one point. It's like a jargon of machine learning.
Okay, okay. In this case, then it doesn't really make sense to use this for verification binaries anyway, because like you're not searching.
I don't think for verification
Yeah.
binaries it will bring you anything. So I think it can be useful for searches. I don't know if people. So there are some papers in ground-based detectors. There are some papers also for LISA, but we never incorporated it into any global fit or realistic setting. So, but I think it's a maybe good thing to try at some point. So here we are going to use do the tutorial which was adapted from one of these tutorials. This is actually very nice tutorials from Michael Katz, so I really recommend you to go and try them. And here we're going to install not a simplified GPU, but a more correct one. So now it will tell us to restart everything, because we need some functionality that doesn't exist in a lightweight version that I have separately. Yeah, so it tells you restart the session. I think it's I think there is some problem is that it installs some packages that has a higher version than the default ones. Okay, here we will force to use CPU backend because I couldn't make it work with GPU backend on the Google Colab. But highly recommend you use a GPU backend in your everyday problems. So we are also going to import all the usual stuff for plotting, etc. Then we're going to also use Erin sampler, and we're also going to use the LISA analysis tool. So this is a kind of like framework that has noise sensitivities and has ways to write it has the likelihoods already there, and also the ways to incorporate your data, noise, likelihood, everything together in a consistent way. So here we're not going to write the likelihood ourselves. We're going just to use the one that is already there. And we take the same galactic binary. Yeah, this is a verification binary, but I just chose it for no particular reason. So we are going to run and plot it. This is the amplitude of the A channel. Then we will also sample lambda and beta, just two parameters. And for the other parameters, we will fix the default values. And here we are going to define kind of a wrapper, a likelihood function. So in this likelihood function, we tell this which parameters are fixed, which parameters are varied. Then we run the waveform with all the parameters. And then we kind of pack this all in the functionality of the LISA analysis tools. So this is our true data, and we also pack it in the similar way as we did with the templates. And then we just put the injection parameters inside the likelihood. Well, this is not enough precision, so it just have to tell you that this is a small number. And then we define our sampler. So here we have two parameters. We define how many walkers we have and how many temperatures. And we start, so here we start with, we can take our parameters that we have from sort of result of the search, put them here, and start the search from the, start the parameter estimation from the parameters that we have found, like close to these parameters. And then we say that we sample for 500 points and that we have a burn-in of 100. I hope that would be enough because we're just estimating two parameters and we're starting close. Not to wait for too long. Because if you remember when Kantan was sampling, it took 15 minutes, so we don't want to wait 15 minutes. Yes?
It uses realistic orbits, right? That's why we.
This one uses Keplerian now.
Keplerian.
You can pass the realistic orbit as input file if you want. And after we do this, I have a small exercise for you, just to play for a couple of minutes. Try to add more parameters and try to sample with more parameters, and also try to, because for parameters you don't know the true values, so try to start with a prior instead of starting with a particular choice of the values. Yes?
When you generate the wave here, the plot. So are we calculating a superposition of galactic binaries, or
this is just one galactic binary.
It's just one. Okay.
Yeah, because they are broadened, so they're not just, it's not a strictly monochromatic signal, but they're a bit broader because of the response.
But the fact that it's very noisy, I mean, I would expect one broad peak, but this is just my intuition.
No, yeah, they're not like that.
Okay.
How to say? So the way they look in time domain is. You kind of you have a sine wave, which after many years would start becoming changing a bit the frequency, but then on top of that you have also the envelope of the detector. So it's not really a monochromatic signal.
Because the detector is moving. Okay.
And it depends on in which frequency range you are. In some they're much more narrow, and in some they're broader.
Okay. Thank you.
So try to add maybe just the inclination. Just try to add one more parameter, and I think that will help you better to understand how these things work. I think we can have time till 12 to try to do this, and then we'll switch to the next tutorial. We started a bit later, so it finishes at 15, right? And at half there is already lunch, so we have to be
Yes, we can move to
20.
Sorry.
Yes.
Could you maybe like elaborate on how, like, I know it's not out there already, but how would we go around doing this global fit for GBs? Do you, like as you've shown, are you going to do frequency batch by frequency batch, and then repeatedly fit the loudest one, subtract it, something along those lines, or?
No, it's so there are at the moment there are two approaches. One is based on reversible jump, as Tas was presenting. So you don't subtract anything, but you just you fit them all together, and then the problem is that you don't know how many signals they are. So you kind of these transdimensional samplers, in addition to the usual moves when you just move and then you accept or reject the parameter, you also have moves when you give birth or kill another signal. So you change your model, and your model changes as if you say, I have one more signal, and then you start kind of sampling like that, and then you see what is your likelihood, and then you can like you would keep it, or you would sometimes you would try to. You have moves when you throw away something, and then you see is your likelihood better if you throw away the signal or not. And then in the end, you have a sort of histogram as the output, because you keep all the samples, but also you have, as a result, a histogram of how many signals you had. And then you kind of say, okay, I take the peak of this histogram, which was, let's say, at 10 signals, and then I cluster my samples, assuming that I have 10 signals. So it's, yeah. And then the other approach is product space, which, if I understand correctly how it works, you do a model selection. So you say, let's say I have 10, 11, or 9, and then you do the estimation for all three of these cases, and then you do Bayesian model selection, and you see which model describes your data best. That's, I think, the other way.
So if we do this analysis, as you say, either of them, and we finish at like month 1 of observation of these cells, half a year, then 1 year later you would have accumulated more SNR. So will you restart the RGM?
Yes, you always, like, you have to keep on running it, because you know the galactic binaries, you won't see probably any of them for first 3 months. You will see none of them, and then you have to accumulate SNR to start seeing them. And you know, the more you observe, the more you see them. So you always have to redo it all the time. So I don't know at which cadence, but yeah. So we finished and we have some posteriors which are not nice because we didn't run for long. Did people try to add more dimensions? Any problems with that? Problems? No? No? Okay, no problems. It's, yeah, all nice and simple. If there are no problems, let's go to the last tutorial. Can I somehow... Yes, so another tutorial would be a parameter estimation in a Bayesian way with machine learning. So the previous one was a point parameter estimation, and this is a Bayesian parameter estimation. The thing is that with this point parameter estimation, in principle, you could have access to the error by looking at, this simulated data and trying to estimate the error from some simulated data spread, but also the network, each weight of your network is initialized by some random number, and then when you backpropagate your results through the network, you update these weights, and so you estimate, in addition to your physical parameters, you also estimate the parameters of this network, and then the errors on these estimation parameters, they couple to the parameter estimation that you get from this regression. So it doesn't give you the correct error measurement. And what is very good, so why we like the Bayesian approach so much, is that it gives us the parameter estimation and it gives us the error that is only defined by the error of the measurement. So there are no other, additional errors. And also there is no kind of all the ambiguity that is there about our parameters. It is all encapsulated in these posterior estimations. So there are ways to also approach this not with the sampling but with the other techniques. In principle, sampling is also an approximation. So we have our bias equation, and then we do approximation by doing the sampling. And we can do some approximation by kind of simplifying our model. And one of the approaches to do this is to use, for example, the thing that is called normalizing flows. It is a kind of, it is a very simple thing, actually. It is just transform from one distribution to the other distribution, which is defined by this change of variable equation. And the idea here is that, let's say we have our distribution that we want to estimate, and we want to approximate this distribution by some kind of, not approximate, but we want to have a simple to sample distribution, and we want to just define the map between these two distributions. And if we know this map, then what we can do, we can just sample from the simple distribution, apply the map, and get the samples from the posterior. So the idea is very simple. In some sense, you can think of that as a cumulative distribution function. For example, if you would sample from the uniform distribution, apply inverse of your cumulative distribution function, you will get samples that are distributed according to the power spectral density of this function. So this is this trick with CDF is like a one-dimensional analogy to the way these normalizing flows work. And the way they work is that if you know the distribution you want to estimate, that would be very simple. You just make a map from one to another. But because you don't know the distribution, but you know the prior, and you can simulate the data. And that what you can say is that you have an access to the joint distribution. So you have your prior, and you have like a joint distribution, which is a prior times the likelihood. And practically, it is implemented as you take a sample from your prior. You simulate the data that is corresponds to this prior. You create the waveform with these parameters, and you add some noise realization, and then you condition the map on this simulated data. And at the next step, like you train it by this kind of pass, and you train it, this transform, to make the resulting distribution normal, which you can think of either as a sort of Kullback library divergence between the distribution and the normal distribution, or it will be the same as maximizing the likelihood. And so basically you need to solve this equation, that's it. You need to define this function, which is usually parameterized as some sort of network. And you need to define this function by design such that it would be a bijection. So you can invert it, and then you can also differentiate this function and its inversion. And basically that's it. And then after you trained it, you create a sample from the normal distribution, you condition it on the real data, and then you get the samples from your posterior. So let's look at the very simple implementation of this thing. Is it clear? So here we are going to use the implementation which is called real non-volume preserving flow. The reason for that is that this normalizing flow is a simple kind of affine transform, which is really easy to implement. So we don't need to use any packages. We just can have like a piece of code in our notebook. It is not very powerful thing, but it is, I think, a good for learning. And here we can kind of, can skip an explanation of these things, because it is the way that we prepare the data is the same as we prepare the data for this point parameter estimation. The only difference is that here, the way we pack our data, we don't pack it like as having channels, but we will just concatenate it along the same dimension. We again have a galactic binary. We do exactly the same, so we have same true parameters. We also vary lambda and beta, and we also sample them from the uniform distributions. We create our training data set in exactly the same way. In the same way, we define our frequency range. We add the noise. We place our templates inside this frequency range. Let's see how it looks. Then we normalize the parameters. We stack the waveforms together. We pack them inside the data set. Let's see how one instance would look like. So here they are just one after another. The reason for that is that we're not going to use CNN, but instead we will use fully connected network. And then we separate this into the, again, training and testing data set. And here is a bit of explanation how this real non-volume preserving flow works. So as I said, it is a simple affine transformation. And then the affine transformation, it has kind of two components to it. One is a scaling, and the other is a shift. And so here you can see that you have the shift and the scaling components. And this T and S, they would be implemented as a network. So this thing is sort of written analytically, and then T and S scaling and shift, we will parameterize as the network. And because this is such a simple equation, we can analytically write the inverse of this equation. This is very important, is that you always need to have a way that you write the inverse of your transform, because this is how you're going to get your posterior estimation. So here we're going to use the so-called coupling transform. This means that some of the dimensions we will keep unchanged, and some we will pass through this transform, and then we need to sort of oscillate through this. So we apply this mask just to say which dimension we are keeping and which dimension we are changing. And then here we define this function T and S that were here in this equation. And here we will define them as just a simple, fully connected network. We use linear layers. The input dimensions would be the number of parameters plus the size of your training data set. So basically what we are just practically doing, we are going to concatenate them together. And the output dimensions will be the number of parameters. So we have two of these networks. And then we choose some values for the hidden dimensions. And the next thing is that we define our base transform. Base transform is this normal distribution from which we are going to sample and then transform it to get the samples from the posterior. And so this is our kind of simple to sample distribution. And then we combine this all together. So here we define the network for this real non-volume preserving flow. And basically, we just implement these two equations, this one and that one. And we define that, so first when we initialize, we start initializing the prior. So by prior here, we mean this base distribution, normal distribution. Then we initialize these networks that we have defined already. Then we do one transform when we have here, we define here the shift and the scaling, and we combine them as was written in the equation. And then we here have a backward transform. So, and what is important that both of these transforms, they are using the same parameters of the network. So when you would train it, you would use, one transform, and then when you kind of test on your test phase, you use another transform. But because they both use same networks, the weights in these two transforms, they're going to be the same. And then we define our training loop. So it is very similar to a thing that we did for the point parameter estimation. The difference is that here is a different optimization function because it's a kind of, you can derive these two optimization functions from the same principle, but here, because you're maximizing the log likelihood, your optimization function is the maximization of the log likelihood. sorry, yes, maximize log value. Same optimizer, and let's train it for a bit.
Excuse me. Sorry, I just thought since we're waiting for it to train, I tried to jump ahead a little bit and try and do what we did on the last one and expand it to another dimension. So I tried to include the polarization. And I know the mask has to be different, but I don't fully understand how that is meant to work.
So the mask, you just need to add additional dimension in your mask.
Mm-hmm.
So here you would say, I mean, this is not the best implementation,
Mm-hmm.
but what you can do is can write like this. I mean, you don't need to write it by hand, but you know, for 3 dimensions it will be harder to write it by hand. But you just write, you know, all kind of permutations, so to say, in your mask. So in principle, you can write all permutations of all possible dimensions for 3 dimensions.
Okay.
You can write it by hand, or you can write it, write a function for that. But yeah, the idea is that usually you would do all different permutations of all dimensions and kind of combinations with each other. So.
But you would not include the permutations where they're all 0 or they're all 1?
No, not this one. So it has to be some. So zeros is when you don't change this variable, and ones when you change them. So there has to be a combination of zeros and ones.
Okay. Thank you.
Still running. We are almost there. If you have any questions at this point.
Excuse me, I have a question. When you define the model, I see you have a list of T functions and S functions. What does each of those functions do? Because I think I understood they act kind of in parallel, each of them on
so
data.
One is sort of like, if you look at the equations in this description, you see you have S function and T function. So one is shift, the other is scaling. So we just is a part of transform, and this T and S is 2 networks, one that does shift and the other does scaling.
Okay, but in the code there are many S functions and many T functions.
Yes.
A list, a module list, somewhere. No, not there. When you define the there, real MVP, when you define the module.
Okay. Sorry, yeah. So because in reality you don't do this transform once, but why it's called flow? Because you combine many transform. And this mask tells you, the mask that you defined here. Here, for example, it would be 1, 2, 3, 4, 5, 6 times this transform. And so this this module list would means that you do this 6 times, one after another.
Okay. But then what is the purpose of using the mask? I'm not sure if I got that.
The mask is to change in this particular implementation of the flow. You have to, is the way they kind of, I think, get the correlation between the different dimensions. That sometimes you fix some dimensions and then you change the others, and then you kind of, for the ones that you change, you combine the information from both dimensions. And this changing of this combination of different dimensions gives you correlation between your different parameters. So that's what called coupling transformers. That's the way they implement it in this method. And we are finished, and I hope it worked. Looks like it worked. And here we just look at a couple of, we take the test data set and we take several samples, and then for this kind of real data, we see which posteriors we get. And so they look, consistent. Maybe not perfect, but at least it is working. And any more final questions? If not, you're free to go.